Thank you, Adolfo, and I would like to thank the organizers for inviting me. I will talk about high-resolution schemes for nano NMR, and my talk is based on this set of papers. So the field of, it's a relatively new field, the field of nano NMR, and the goal of the field is basically to do the following. So what you see here is an NMR machine, and it's a clinical analog, the MRI machine. And in the end, the MRI machine gives you a three-dimensional picture, and which is based out of voxels. And the size of the minimal voxel per square root of hertz is around 10 to the 13 spins. And what the nano NMR setting wants to do, the final goal is to decrease the minimal number of spins down to a single spin. And what is the idea? The main idea is to use diamond. And so we can use diamond and somehow put an NV close to the surface of the diamond, or a set of NVs, ensemble of NVs. And then let these NVs, these artificial atoms that live in the crystal, the artificial ions, to serve as sensors of magnetic field. And then to put something on the surface, so it could be eventually, the final goal is a single molecule, and to get the image of the single molecule in real time. Or a bit of a less challenging task, but also very challenging, is to do an NMR of a substance, of a small amount of substance, tiny amount compared to regular NMR, but still not single spins. And then just to get the NMR signal, suppose here, so I put blood. You don't usually do blood tests in NMR, but suppose you want just to get the spectrum of whatever you put in there. So I'm a theorist, so this is the experimental platform. I'm a theorist and I do theory for this, and right now I'm concentrating on signal processing. So what do theorists do? So if we go, this is a typical NMR output. So you see the spectrum of the NMR, the Fourier transform of what the NMR reads, and you see peaks. And each peak like this is actually a few frequencies. And the information is actually, I see here a bunch of frequencies. The information is actually in the difference between the frequencies. It can be chemical shift, so it can be J coupling. So it's a Larmor frequency of the same substance, but just because it's located on different places in the molecule, it will have a bit of a different frequency. And if we can measure this frequency, if we can estimate it, we can get a lot of information, which is crucial for many chemical and biological goals. So signal processing was very influential in NMR, and what is the final goal? Suppose we look at this point here, and we just look at the Fourier transform. It will look something like this. It's very difficult to get information from this picture, but if we use some kind of signal processing algorithm, we can maybe get something like this. Here we already can see 4 peaks, and if we use even a better algorithm, we can see something like this, and from this we can extract the information with very good accuracy. So what I'm trying to do, it's a series of projects. We're just starting. We have some results. We're continuing doing this. So I'm doing the theory, and Fedor Retzker from whom is doing the experiments. We're trying to see how far we can push it and what are the limits. Especially the goal is to understand what is the difference between a quantum system and a classical system in terms of both of the substance, but suppose even the simplest question that the signal is classical, is completely classical, and we read it once with a coil, with a classical system, and once with an atom, what would be the difference, and can there be a dramatic difference? So what do I mean by classical and quantum? I'll show you, explain you why later, but of course one thing in quantum is entanglement. We don't want to look at this stage. We want to look at the simpler effects that we can already measure now. One thing is, there are 2 time scales. In the end, quantum, in the most basic things, in a few basic things, one of the basics is coherence. So we have a coherence time of the NV, which is the probe. So it has to be long to get good results. And we also have the coherence time of the substance. So this is, in the end, this thing produces some classical, we can think of it classical magnetic field. And it also has a coherence time. Now, whenever the coherence time of the substance, the signal is much longer than the coherence time of the NV, I will show you this more or less can be treated as classical. So whenever the T2 of the detector, here the NV, is much shorter than the coherence time, let's call it T2 or T5, the coherence time of the substance, then we we can call it classical. So of course we can argue what is classical, what do you mean by classical, but at least from a very practical point of view, all the signal processing algorithms, the classical one, can be used readily, and we're going to get the same results. Okay? But if the coherence time of the quantum is longer or is in the time scale of the substance, we need new algorithms. Maybe we can get much better results. The other thing, when we compare quantum to classical, is the noise. So if you think about an NMR machine, a classical or a Lagrange NMR machine, in the end there is some magnetic field, which is read by induction method. So the coils here gives us a signal, and there is noise on these coils. Because it's a large system, it's usually a Gaussian noise. If we have a single atom, NV, or a few of those, the noise is a Bernoulli. So it's a Bernoulli process. We get either 0 or 1. So this is the most basic quantum thing. And I will show you if it is quantum, then there is a huge difference between quantum and classical. What is the basic? First, what is the basic thing in quantum sensing? And the basic thing in quantum sensing, if we have some energy gap, we want to estimate the energy gap. The energy gap can be a function of magnetic field or something else that we want to estimate, some classical parameter. So we make a measurement, and in the end, the probability to be in the up is a function of delta omega that we want to estimate. And how do we get information out of that? So one thing, there is, of course, the noise, the Bernoulli noise, the 0 and 1 noise, which is a bad thing. And there is the derivative of p with respect to delta omega, which is a good thing. The noise is just p multiplied by 1 minus p, and it looks like this. Yeah? So of course, the noise is maximal at 1/2. We don't know. We have very little information about the next trial. And the noise goes 0 at 0 and 1. So there's no noise here. And in principle, first thing when I looked at quantum sensing, I thought, well, this is a great thing. If we work relative close to these points, we can actually gain quite a lot. But it's usually is not the case. Well, I'll show you an example here where it is the case, but I don't know of any other example in which we can actually gain by these points in which the noise is 0. The reason for this is that also the derivatives behaves in the same way. It is true that the noise here is 0, but there's also no information because the derivative here is 0 as well. So the derivative will be something like this, and when we divide the two, we get something which doesn't depend if we measure here or we measure here. And because of practical issues of other noises, usually it's actually not so good to measure here. So to summarize, we can also look at it in a different way. So there is, this is maybe the pessimistic way to look at this, but the optimistic way is if we look at the derivative, there's lots of information here, and there's no information here. So you would think this is a bad point, that you don't want to get to this, you don't want to ever get to this point, but because the noise is also 0, this saves you, and in the end you get a good result. As good as here, but still you get a good result. So in principle, the question that I try to pose is, can we actually use these points to increase resolution? And it seems that for resolution, we can use these points and get a huge amount of increase compared to classical noise, compared to Gaussian noise. In the end, when we divide the two, we get the following formula, the quantum sensing formula. The uncertainty goes as 1 over square root, the number of atoms, the time, basically the number of measurements. So this is just the 1 over square root of n. 1 over square root of n scaling plus 1 over square root of the coherence time. And this is the reason that we want to prolong coherence time. And for this, dynamical decoupling is done. So the first question we want to ask, what is the role of T2? So of course, this is in the end, this is the coherence time will be limited by T2. And of course, short T2 is bad and long T2 is good. But the first question, what is bad and what is good in this sense? So suppose this is the spectrum. This is what we see. This is the best thing we can get. What does that mean? So this is for long T2. When T2 would be short, this would look much worse. But there are two possibilities. It can look much worse in this sense. So there's going to be less SNR. It's not going to be exact. We're going to get lots of information, but we'll still look something like this. And this is, in a way, looks like a good noise. Yeah, we know we can somehow overcome it, maybe making experiments longer. On the other hand, if it's a convolution noise, if it's an integral noise, it will just smear this function, will create something like this. And this is going to be a problem, a much bigger problem. It's also, in the end, it's called the resolution problem. And the first thing, what is T2? Is it noise of this sort that we can actually do something about, or is it noise of this sort? So the first thing, what is usually done is dynamical decoupling, and dynamical decoupling gives us this formula. It also was in the talk of Lorenzo Viola, also I guess in other talks. This is the integral between the power spectrum and the window function or the filter function. Yeah, so this is the power spectrum. We want to read it, and we make the experiment, and then we see, and this is the window function. We get this integral, so we get a result about this. Yeah, if we change omega, we get a result about this, and in this way we can reconstruct the frequency or the power spectrum. And it is limited usually more or less, but something which is 1 over T2. So we look at this way, then T2 is noise of the bad type, because it's an integral. We are doing an integral over this. If there were some peaks here, it would just integrate over them. We just get one single value. It's very, very difficult to construct it after a noise of this type. Okay, so it seems that T2 is a noise of this type. So I'll show you that in principle it is actually noise of the other type, or at least a more complicated noise. But first I would like to make a recap of the resolution problem. So what is the resolution problem? In the essence, it's the same problem as optical resolution. So we have two emitters or two frequencies. We look at the Fourier transform. If we look at the image, we see something like this. This is from the first emitter of the first frequency. This is for the second. I put here colors, but of course there are no real colors. But here, no problem. We can look at the Fourier transform. We know there are two frequencies. When they are closer, again, we don't see the color. We see like this. Okay, can still differentiate, but the problem starts. And when they are closer, so the Abbe limit or the Riley limit, then we see something like this. And this is a problem. So here, from here, it's very difficult to find that there are two frequencies and what are the frequencies. This is called the Riley curse or the resolution limit, the Abbe limit. So put it in... For numbers, let's assume the simplest model when we know there are two frequencies, we know what is the noise, we know what is the two or the noise in each frequency, and let's make a calculation. So there is sigma is the noise, delta is the difference. Suppose in the limit when delta is much smaller than sigma, this is just going to be a new random variable which is more or less Gaussian. We can estimate its noise, and from this we will know that the uncertainty in delta, which was for one frequency just sigma over square root of n, will be sigma over square root of n multiplied by this factor, sigma over delta. And this factor will diverge when delta will go to 0. This is usually much worse. So the power here, it's 1, according to this naive calculation. Usually we don't know sigma, we don't know other stuff as well. This is much worse than 1, and in the end, it is unpractical actually to deal with this. And this is what is called the Riley curse. Now, for two frequencies, so there is one frequency, and suppose we see one frequency with noise, we can estimate this frequency is going to be some constant divided by square root of n. But if there is another frequency next to that, the uncertainty in this frequency will be the same constant divided by square root of n plus some factor that goes as 1 over omega 1 minus omega 2 to the power of alpha. And this, of course, is a divergent factor, and this is the Riley curse. And there have been many, many algorithms, both for imaging and for signal processing for NMR, to deal with this problem. And there are some results, of course. But this is the issue that I would like to talk about today. So first, this was in this paper, the experiment. So we done the analysis for this. The experiment was done by the group of Fedor and Retzker, mainly by Liam McGuinness. And the idea is the following. So we call it Q-dye. Others have different names. I'll to mention the others. Suppose we look at a magnetic field that oscillates like this. Now, we are doing dynamical decoupling. So actually what we see is not the frequency of the signal, but the frequency of the signal minus some omega frequency of control or actually of dynamical decoupling. So we always see just the differential frequency. This is already one advantage that we have. We can basically, instead of looking at the high frequency, we can subtract any number we like or add if you want to. So suppose this is the frequency and we make a measurement. So T2 is very short. And from this time here, from this area, we want to estimate the frequency. Of course, it is very bad. It's very difficult to estimate the frequency from here. And if you look at this, at the filter function picture, what we see here, so I'll always prefer to go from the Fourier, from the frequency space to the time domain, in which the intuition, I think, for this is better. So this is how it looks in the time domain. How does this problem looks in the frequency domain? It looks like this. So this is the power spectrum. This is the filter function. This is the T2, and we have a problem. Yeah, it's very difficult to estimate the frequency with a filter like that. So what do we do? So we actually can look, and this is the idea here, to look at a relatively classical method. We don't have to estimate the frequency from here. we don't have to look at this integral in a way. We can just estimate the magnetic field at this point. Now, the role of optimal control, I would like to say, it's not only to increase T2, but it's also to subtract this number. So we can look at every frequency we like. We can always subtract. That can be important later on. But what we can do, we can just measure the magnetic field, not the frequency here. Now the magnetic field, so this point we can measure with good accuracy. There's no problem of resolution or anything like this. We can also measure the magnetic field at this point, so the average here. And then by looking at the correlations, we can get a resolution which is very, very good. Because now in the correlations, there is lots of information. And the experiment is basically done like this. Suppose this is the magnetic field. The control can be done continuously, can also done by pulses. So suppose we make the pulses, we know the frequency exactly, we make the pulses exactly at this point. So of course, if the function is like this, we only see the integral would be 0. But if we make pulses at this point, we will see actually the absolute value. So we'll see this plus this plus this plus this if the pulses are exactly at this point. So the phase would be large, and also the number of photons would be large. But because we don't know the frequency, when we make a measurement again, we're going to miss this point because we don't know the frequency. It moved a bit. So we're going to see a bit less photons. Or we're going to get to this point when instead of making the pulse here, we're going to make it pulse here. We're going to see a 0 phase and no photons. And in the end, if we look at the number of photons, it will behave something like this. And when we Fourier transform this, we get a very, very sharp peak. This is the peak that we get in the regular dynamical decoupling way. With the convolution, you see this is much, much sharper, and the resolution is much better. And this is by just correlating the point here and the point here. And in this correlation, because the time is long, we use all this coherence between this long time. Of course, we get a much, much better result in terms of resolution. And these are the experimental results. This is the regular method. The width is very large, 300 kilohertz. And here the width is very small, 600 microhertz. Okay. So together with us, there were another two groups who done something which is connected. The group of Christian Degen done something very similar. Also, the group in Harvard looked already at chemical shifts, at real measurements, and this could see chemical shifts with this method. So we've done the analytics, so we looked at the Fisher information of this process, and this is what we found. So what will be the uncertainty in the end? The uncertainty would go as 1 over omega. Omega is the strength of the signal, the strength proportional to the strength of the magnetic field in units of hertz. And the total time, so goes the square root of this time, the T2, and the coherence time of the signal, T phi. This will be the uncertainty after Fisher information analysis. Now, if the coherence time is very long, on the order of the total time of the experiment, we will get a new scaling of 1 over t to the 3/2. So we also can compare it to ideas from NMR, and there is lots of similarities. The algorithms are very strongly connected in this regime. The reason for this is, go back to this thing. The reason for this is, in the end, we are measuring the magnetic field here, the magnetic field here. That's exactly what the NMR machine measures. So in principle, we can take all these signal processing algorithms in NMR that were developed for many, many years, and we can use them to tackle this Rayleigh's curves. But still, in NMR, this is still a problem, the resolution problem. Okay, so what I show you, the T2 is probably not a noise of this type, is a noise of this type and not of this type. But what about the coherence time of the signal? This still looks as if it's noise of this type. And what I will try to show you here, that actually for the NMR setting, in some regime it is not, and it's also noise of the good type. Okay, so back to the resolution problem. This is the problem that is shown in the frequency domain. I would always like to go to the time domain, in which the intuition for this I think is much better. Going to the time domain, we would like to look at two frequencies. For two frequencies in the domain, we're going to see a bit note. So there is this frequency, which is very high, which is very easy to measure, this large frequency, but this is not a problem. But the bit note is very difficult to measure because it's broad, meaning we don't have enough coherence. We can't measure it for a long time. If we have enough coherence, we can measure the bit note, no problem. But if we don't have enough coherence, T phi is short, it's like this, we actually have something like this. And from this, very difficult to estimate the bit note. Now, this looks, again, as a problem of the bed type. Yeah, so if we can only correlate this, and this will create a problem for us. And it seems that this is the problem of the bed type. This is what we thought at the beginning. But now, let's look at what happens in NMR. Why in NMR it's actually a problem of the bed type. Of course, we can do things about it, but it's still a big problem. Now, in NMR, suppose there are two frequencies. They always start in NMR. We use some polarized substance. We make a pulse. And all the spins are starting to rotate. So they all start with the same phase, either two sines or cosines or the same phase. But if we add two sines, we're just going to get two sine of the addition, omega 1 plus omega 2. To estimate omega 1 plus omega 2 is not a problem anyway. We can just look at the Fourier transform. But the omega 1 minus omega 2 multiplied by t is always in the cosine. Because it's a small number, the coherence time is short compared to omega 1 minus omega 2. The cosine equals to something like this. So omega 1 minus omega 2 goes always in second order, which means it doesn't matter what you do. The maximal information is here, and you have a problem, because it's always in second order. But if the phase is not the same, of course, sine plus a cosine, the omega 1 minus omega 2 will be in the sine, and then it's not clear if it is actually such a big problem. Now, what is the difference between nano NMR and regular NMR? So I showed you some differences. But the first difference will be because it's a small amount, at least now in most experiments, it's not polarized. So what we actually measure is statistical polarization. It's a small amount, and we measure the signal of the, not of the n, but of the square root of n. Of course, in regular NMR, square root of n over n is a tiny number which you can't measure, but here the numbers are small, and you actually can measure the square root of n effect. And this would be different. So what happens, the NV is close to the surface, and the molecules, they just diffuse like this. Because they diffuse, each time we measure, they come with a different phase, because it's unpolarized, the statistical one. So there is large phase noise. But what I showed you before, the problem in NMR, all the frequencies comes with the same phase, and this is a problem. But if they come with a different phase, maybe we can gain something. It's not super surprising, because we know if we look at super resolution methods from imaging, we know that noise is a good thing. Either SOFI, which uses higher correlations because of the noise, or STORM, noise is always a good thing. And the intuition here is at some point, if you look at this and there is a random noise, so there are two emitters, but sometimes this works, sometimes the other one works, and like this you can resolve. Can you do something like this here? And what we've done, so I won't talk about it too much, I'll just show you that it works. We designed, but we still call it a classical algorithm. Exactly because of the fact that we measure, in the end we use the magnetic field, and from this we construct an algorithm. So it's a classical algorithm that didn't exist for NMR, because there everything is polarized. But here we constructed a classical algorithm based on the intuition from these imaging, super resolution imaging methods, and indeed we managed to overcome the problem. So how does it go? So we make many measurements like this, looks at the correlation, but the phase keeps changing. So we make 4 measurements, the phase change, we make 4 measurements, the phase change again, and like this we continue. So we design a Bayesian method that actually can overcome this problem. It's not a regular Bayesian analysis. We have to find a special function to fit it to, which is not the real function. But somehow in this way we managed to overcome this. But we made a Bayesian algorithm, so a signal processing algorithm based on Bayesian analysis and Bayesian numerics. And in the end, this is what we get from the maximum likelihood function. And it seems, and we also showed analytically by calculating the Cramer-Rao bound, that this problem does not exist in this setting. So what you see here, this is numeric, this is the Fourier transform. This looks quite bad, around the 1000. And what you see here, so this is what you see from the Fourier transform. This is what you see from the numerics. We can actually see the two frequencies very good. Then the problem is with Bayesian methods, people in signal processing usually they use better methods numerically. I mean, they're very good analytically, but they're problematic numerically. So we teamed up with numerical guys that managed to improve the numerics, and they can also see 3 and even more frequencies like this. What you see here, this is the numerical results. So this is the results that came from the Fedor group. They created a signal. They didn't tell us if there is 1 frequency or 2 frequencies there, and we had to estimate to find how many frequencies they are and what are the frequencies. And here you see, this is the Fourier transform. This is the line here, and here you see our signal processing method that actually sees the 2 frequencies. Okay, I won't talk about the method so much because I want to concentrate on the quantum classical thing. But again, I would like to stress in the end, this is a classical algorithm. So we basically produced a new classical signal processing algorithm. It wasn't there before because the noise in this experiment is very special, so we analyze this noise. But can we do something which is quantum? Okay. And in order to see how can we get something quantum, let's look. We know there are quantum algorithms, at least in Gedanken experiments. And so what I show now, suppose we have the following question. We know there are one out of two molecules, either molecule 1 or molecule 2. So molecule 1 produces, suppose, this spectrum, the blue one, and molecule B supposes the yellow spectrum. So we know this is one of those. Can we find which one? What is the best way to do it? Classically, we just find the Fourier transform. We just look at the power spectrum and see which one it is, makes a fit. Quantum mechanically, we can do something else. Let's just simplify the problem to one frequency. It doesn't matter, whatever function it is. And we can do it like this. We use control. We start with the spin in this direction. We do the control in the following thing. We add control in a way that if it's molecule A, the spin rotates in one direction. If it's molecule B, the spin will rotate in the other direction. And then it's enough to make one measurement to decide. Now for this, there is no classical analog. This is a quantum estimation parameter. It's quantum estimation method. There's no classical analog to this. Of course, the question, can it be better? Can it be much better than a classical one? Usually up to now, there were no evidence of this being much better. The time is just goes as 1 over square root of omega, the strength of signal, omega 1 minus omega 2. It's not limited by 1 over omega 1 minus omega 2, by something different. Okay, so first, this is connected also to estimation. And but first, for discrimination, let's look at the calculation itself. We have H1, we have H2. The phase difference between this and this dynamics and this dynamics will go in the following way, in the limit of very short time, in the problematic time. And in the end, the phase difference will scale as omega is this way, t squared. That's why we have the result here. We can also use the same method, not for discrimination. I always want to use this. What I want to say is I want to use this intuition from discrimination and to use it for estimation, because in the end we want to use estimation, which is much more of a difficult problem. For estimation, it will behave the same way. So we have a Hamiltonian. We go for short time. Suppose it's a sine. We go for very short times, this omega delta t. Now the phase is the integral of this, and the Fisher transformation is the derivative. So the phase goes as t squared. The Fisher transformation goes, in the end, as t fourth. And this is a quantum thing. And it's the same function as for the discrimination, which is quite sure is quantum. Now let's go back to the quantum and classical. So here, when we go to a thing like this, it is better to measure the magnetic field, not the frequency in each point, then make a regular signal processing analysis. This would be classical. But if it is something like this, then we have to measure the frequency from a single measurement, and this is really quantum. There's no classical analog, or at least technically, this is not the way it is done classically in any way we know. In any system we know. So this I would call quantum. So the experiment of the estimation and discrimination was done by the group of Fedor. So I have a bit less time than I was hoping for. So just I explained the intuition. Suppose this is the field, and we make, so this is omega 1, this is omega 2. We make the pulses not exactly at the crest here, but between omega 1 and omega 2. So if we made it a bit before this, we still acquire the phase, this green one. And here it's going to be a bit after, we will acquire the phase, but in the opposite sign. And in the end, the spin will rotate left clockwise or anti-clockwise if it's omega 1 or omega 2. And at some point, there will be orthogonal. If we measure there, we can discriminate between the two frequencies. And this is how the phase, the difference in the phase behaves. These are the experimental results. So this is the discrimination thing. Here you see the phase goes as t squared. And here is the population. So as we increase the time, it becomes more and more orthogonal until in the optimal time, the time I showed you before, it is almost orthogonal up to experimental imperfections. And this is the number of measurements that we need in order for distinguishing. If the time is short, then we need lots of measurements. In the end, it will be very connected to what we get in the classical algorithm, more or less the same number of measurements. But the longer the time, the more coherence we have, we go down to the one measurement, and for this there's no classical analog. Now we can also do the same for estimation. And what you see here, this is for estimation. This is the optimal detuning. So depends on the interaction time. There is a difference optimal detuning that will give us this scaling. And what you see here is it's first if we can actually make. So I told you that we have to use the fact that the signal is a sine. If it's a cosine, it doesn't work, right? Because if it's a cosine, it is not linear in delta t anymore. So it has to be the sine. So if you make the pulse exactly at the sine, then we get a very good scaling. If we make it randomly, if we make it at the cosine, we get a very bad scaling. If we do it randomly somewhere, we still get the same scaling with time, but it is by factor, but by factor it is worse. So this is the numerics, these are the experimental results. And what you see here, okay, if it's a cosine, it's just the noise kills you. But if it's a sine or the average, we still see a nice fit and that's correspondence to the experiment. So this is the T4 scaling. Just I would like to explain again what we see here. So I showed you before. So if we can measure only the sine, so we can always start here, then we get the very good scaling. The point is that as we see from here, the quantum algorithm is the worst algorithm. It's better just to use a classical algorithm just to measure the magnetic field and then to correlate. So actually, this nice scaling is not really useful. But what we actually have, if the noise is like this, it's very noisy. So each time we make a measurement, it's a different phase. Then what we get here, and the scaling is the same. So this is the idea behind the T4 scaling. So first we notice this just by looking at this formula, and we can also do calculation. When T2 is long, we get T4 scaling. And this T4 scaling on certainly is T2. And so this was, then we were looking and we found that actually there was a paper this recently by Andrew Jordan. And from this paper we got ideas how to extend this. And we looked at the incoherent case which I showed you before. And actually, in the end, this T4 scaling is not, so it's very nice to understand, but it's not much different than actually what is done anyway. What it means that if this is the frequency, and this is the noise in the frequency, the optimal point of measurement would be just here, right, on the end of 1 over the detuning. And if you look at regular frequency measurements, they always scale in this way. Okay, but what can we do? So this is the effect of coherence. So what we see from here is if we want to get a better algorithm, up to now there's no better algorithm, this is just the understanding. If you want to get a better algorithm, first we have to go to the limit in which the coherence time of the qubit that is used to measure is long. So this is also quite intuitive that the quantum limit is somewhere here, or the noise is large. What about the other effect, the Gaussian thing, the noise? So the noise here is Gaussian, and the noise here is a Bernoulli noise. So what could be the effect of this thing? And the classical signal, suppose we have two frequencies, the classical signal would be sinus omega 1t plus sinus omega 2t. Let's assume that it is the same single strength. Because if the single strength is different, this makes the problem easier. There is another parameter which is different in which we can differentiate between two frequencies. Let's suppose this is the toughest problem we have, and the signal is actually the same signal. So this is what an NMR machine sees. It sees two frequencies with a Gaussian noise. What happens in the quantum NMR machine? So this quantum NMR machine, which is based on a few single spins, it depends what is the noise. We can add more, but still the noise has to be small to add more. We in the end see a Bernoulli noise. So the probability to get 0 or 1 would behave in the following thing. So just the integral of the magnetic field, so the integral of this thing, so sine square of the integral of this thing. And so first, when we noticed this, it was some time ago, we noticed this that, so when kind of studying signal processing, and we looked at this, and it looks completely different. Yeah, it's a completely different noise model, and if we want to overcome the noise, it seems that it should behave in a completely different way. The quantum should behave in a completely different way from the classical. And I was talking to people from signal processing, and they say, wow, this is, I never seen something like this, should be completely different. But when we start analyzing this, and in most cases, we actually get the same result, up to what we found now, which is really different. But in terms of signal processing, we have this process with a different kind of noise. So here, the noise, it's a Gaussian noise. Here, the noise is in the signal. Would it have dramatic consequences for estimation? One thing which is important, control has an important role here. So delta 1, delta 2, these are not the bare frequencies. These are the frequencies minus the frequency of the control. And of course, we can put any control frequency we want. Omega 1, and there are two quantities here. There is omega 1, there is omega 2. It is better to look at the subtraction of those, and the addition of those. It's better to look at omega 1 plus omega 2 and omega 1 minus omega 2. And because it's multi-parameter estimation, but one parameter is very easy to get. So omega 1 plus omega 2, it's a parameter that's very easy to estimate. We just look at the Fourier transform and we see a peak. It's very easy to get omega 1 plus omega 2. Omega 1 minus omega 2 is a parameter which is very hard to estimate. This is a parameter we want to estimate. But when we look at any sort of estimation, definitely Bayesian with the Cramer-Rao, it's always better if there are two parameters. It's always better to go to a basis, to rotate to a basis in which one parameter we can know with very good accuracy and then just forget about this parameter. So it's always better to go to delta 1 minus delta 2 and delta 1 plus delta 2. Okay, so I will do it in a minute, but okay, this is the Hamiltonian. This is the probability. Now remember, these are the phases. The phases are random because we don't know where we start. Yeah, we don't know what the phase of the start of the measurement. If we would have known that, it would look something like this, and then we could use a classical signal processing algorithm I showed you before. So it's also intuitive. The quantum has an advantage I showed you before only when the coherence time is long enough. And what does it mean long enough? It's long enough compared to the other parameter in the problem, which is the coherence time of the signal. But that's what it means. So we are in this regime, which means we have to average. We can average over the frequencies. And usually in signal processing, it's always crucial what you can integrate upon and what you cannot integrate upon. That changes the algorithm quite a lot. And actually also in the algorithm, the classical one, which I didn't go into details, this was the crucial part to understand what we can integrate upon and what we cannot. And with some luck, it can start working. But here we have to integrate over the phases. There's no, we cannot estimate them. When we integrate over the phases, we get the following probability. Okay, so let's look how it looks. Let's see how it looks like. This is the probability, and now we can change exactly as the dynamical decoupling works, dynamical decoupling protocol for estimating frequencies work. We have the qubit, and we drive it with some frequency, and we get the signal, and this signal should be proportional to the power spectrum at this frequency. So let's do the same experiment here. Let's just drive it. So it's very easy to see. We just, instead of delta, we say delta minus delta control. We change it, and that's what we see. So this is if t is short. This is the unresolvable limit. Oh, let's start here. This is if t is long. If we change dynamical decoupling frequency, it means here just to delta 1 minus delta 2, subtract some number out of it, this number, but we see that the function behaves in this way. So we see two nice peaks, the two frequencies. Exactly as we would expect in this regime, in which the coherence time of the signal is long, and everything is good. What happens in the other regime? When t is short, we see just one frequency. So again, we have the problem, and that's what I mean. In the end, it looks like completely different. You can overcome many limits, but in the end, you do a calculation which is completely unrelated to the other one, and you get something which is exactly the same. So in the end, it's not so easy to get something which is quantum. Maybe it is not so surprising. We know that from other examples as well. But now there is a twist here, and the twist is the following. Let's write this probability as a function of delta R and delta S. Delta S is omega 1 plus omega 2 minus control. And delta R is delta 1 minus delta 2. You should subtract the control, but it's the same, so it doesn't matter. So delta R, it is the difference between the two frequencies. This is the important parameter. Delta S is the sum minus the dynamical decoupling drive frequency. Now what happens here? Now we can expand this around delta r, and if we expand the probability around delta r, we get some function of delta s plus some other function of delta s multiplied by delta r squared. It means the derivative goes to 0 as delta r goes to 0. Yeah? So this is what we see here. In the end, it goes to 0. So it seems that we have the same problem again. That's how the problem looks here. But now we have control. We can do with delta s, which is the sum, we can do with this whatever we want. Because it's a nonlinear function, this function will have many zeros. So we can just change the detuning until this function goes to 0. And why does this help? If this is 0, now we go back to the original problem I showed you about quantum sensing. That what happens in quantum sensing, in the regular quantum sensing of the magnetic field, the derivative at these points goes to 0. Or there is the other way around. Yes, so we see that the noise, we go back to the p multiplied by 1 minus p square root, goes to 0 at these points. And you think, that's why I thought at the beginning when I learned quantum sensing, wow, this is great, I can use these points, but you can't because the derivative is 0. Here's the other way around. So we see the derivative is 0. This is the source of the problem. But now the Bernoulli process gives us a solution. Just look at this point, and we know that this derivative, that this divergent because of 0 derivative will be saved by this point. So what happens here? So again, we go to the 0 point. This is the probability. The derivative is linear in delta r. The noise, the square root of 1 minus p multiplied by p is more or less p. Also linear in delta r. When we subtract the two, delta r is out of the formula, and the resolution is saved. So in the end, the uncertainty in delta 1 minus delta 2 is just some factor, 1 over omega t2 square. Again, the t2 square, 1 over square root of n, and n is the number of experiments we make. So the total time divided by t2. And the important thing that there's no resolution problem. The difference between the two frequencies is nowhere in this formula. So suppose this is omega t2 is the coherence time, omega is the strength of the signal. Suppose they're more or less comparable, so it's more or less 1. So we go back to the simple equation that we get from regular quantum sensing, 1 over square root of t2, square root of the total time. And it seems that there is no resolution problem, and the Rayleigh curse is bypassed. It's also important that there's no very complicated signal processing algorithm like I showed you before. Bayesian is usually sometimes effective, but the problem gets more and more complicated in the end. Bayesian, because of numerical problems, doesn't work. All we have to do here is just the simple experiment, the simple analysis of quantum sensing. We just have to count the number of photons and then to look at the average. So there's no complicated numerics here. So in the end, it seems that the Rayleigh's curse is overcome. So if classical, there is a divergence for two frequencies, then quantum, we managed to erase this term altogether. So this is the theory. This we've written in the paper I showed you, and now Fedor is doing the experiment, and hopefully it will work soon. Just before I finish, just to get some, just to explain this thing, suppose, not to explain how surprising it is, suppose we look at some kind of fluorescent material, depends the amount of light depends on the angle. By collecting photons, we can estimate what is the angle. Of course, it doesn't matter classically if we put some more substance here, or we just put better lenses to get more photons. We will get the same result. But quantum mechanically, it matters, and that's exactly what happens here. If we put better lenses, we can estimate, in this example, the angle much, much better than putting more substance here. So this is really surprising, and it's really quantum mechanical due to the Bernoulli distribution. So before I thank you for your attention, I just mention the people who worked on this. This is my group. The two guys who worked on this, Amit and Tuvia. Tuvia done most of the theory. Was really exceptional in this problem. The experiment was done by the group of Fedor Yelesko. So this is Fedor, Liam, who was running all these experiments, and Simon. And in the end, with the numerics, with the Bayesian numerics, when it got too difficult for us, these two guys, Javier, in the group of Javier, they helped us, and they've done the complicated numerics of many frequencies. And with this, I will thank you for your attention.